Good morning, everybody. So I want to make a quick little video because obviously you've just finished chapter 6, so I don't get to introduce you guys to chapter 7 live and in person, but we can at least do a quick video to introduce some of the key concepts of 7.1, which is on exponential functions, growth, and decay. So what I want you guys to do for this asynchronous day is if you are able to print the notes, you can print them and fill them in. You can add these notes to your notebook, or you can digitally annotate these notes via Cami, iPad, Apple Pen, whatever you guys use. So treat this like we're taking notes just like in class. All right? So a couple of vocabulary pieces to start. We have two diagrams that represent exponential growth and exponential decay. So what is the equation A times b to the x power? What do those letters represent? A represents the initial value. B we call the base. B is also going to be talked about as like almost think of it as like the growth factor. We'll talk about that in a little bit. X is the independent variable. Obviously, that's going to be y is our dependent, or f of x is our dependent variable that will be affected by the independent variable x. So key vocabulary when we look at these graphs are something called an asymptote. Now an asymptote, we can actually see this in our kind of faint picture up top. An asymptote is a line that a graph function approaches as the value of x is very large or very small, but it never actually hits. So this graph, it actually looks like it hits the x-axis, but it really doesn't. It actually just approaching it so microscopically that it's almost indistinguishable, but it just gets very, very close to the x-axis on either side. So it's just going to get very, very close to the x-axis. It actually never technically hits the x-axis. That's why it says the word approaches there. Asymptotes are going to be a very important part of this unit as well as pre-calculus next year. All right, so it's an idea of that it gets close to a line but doesn't quite hit it. In this case, that line we're talking about is y equals 0, or the x-axis. Now, there's two types of exponential functions that we're going to study right now. There's exponential growth and exponential decay. In exponential growth, the b value, the base, is a number that's greater than 0. And growth, as the x values go up, the y values grow up. All right? In decay, the base value is a value that is in between 0 and 1. So it's like a fractional amount. Okay? And obviously that would indicate as my x values go out and out and out, my y values are decreasing, exponential decay. So we're going to be looking at the graphs of these functions. Now, obviously I'm not going to just sit here and wait, so I would encourage you guys to pause the video to then investigate the graph on your own and then hit play when you're ready. You can figure out if this graph is going to be exponential or exponential growth or decay based on the b value. The b value is 3/4. Well, that's a value that is in between 0 and 1. So because it's a value that's in between 0 and 1, this should represent exponential decay. Oh, little spelling error there. Fix that. Now, once we have exponential decay and we know that's going to be exponential decay, go ahead and use your graphing calculator or Desmos to then put it into your graph and see what it looks like. It actually is going to look like this. It's going to show that exponential decay. Now, you can use Desmos or a graphing calculator to help you get some points to help you make this graph. For example, 0, 10 was a point. And there's a bunch of decimal points that I had to use to kind of approximate. But okay, use your graphing calculator to help you out. Again, pause this video at any point to give yourself more time to practice or to look at Desmos or a graphing calculator. In my next example, my b value is 2.5. Well, that's obviously a number that's greater than 1. So in this case, we're going to have exponential growth. Go ahead and put that in the Desmos or your graphing calculator and try to replicate the graph on paper. We're going to see exponential growth. A couple points that I used to help me graph was I used 0, 4, and 110. There's also some decimal values that I use to kind of approximate that graph as well. But I can see exponential growth. The function's rising at an exponential rate. I can also see the asymptote. See how it's kind of curved at the end? I'm trying to represent that this line doesn't actually hit the x-axis. It kind of just runs very, very close to it for infinity. So it gets very, very close to the x-axis, but doesn't technically cross over. Now, I already wrote down the function for percent increase or decrease. A of t equals a, 1 plus or minus r to the t power. A of t represents the final amount. The little a represents the initial amount. R is the rate of increase or decrease. We just put / decrease. And we are going to have that in as a decimal. So not, if it's a fraction or a percentage, we're going to convert that to a decimal. And t represents the number of time periods. Little hint for you guys, notice we have plus or minus up here. Depending on the context of the problem, which we'll talk about in a second, we're going to use plus if it's percent increase and minus for percent decrease. So check out this example. We are going to use our graphing calculator. Again, if you want to use decimals, that's fine, but I'm going to show you guys how to answer this using a traditional graphing calculator. Clara invests $5,000 into an account that pays 6.25 interest per year. How many years will her investment be worth $10,000? Well, let's look at some of these key values here. We know that she's going to start off with $5,000. Her bank gives her 6.25% interest per year. This is exponential growth. Her money is going to be increasing in her bank account. We are trying to figure out when will her bank account reach $10,000. So putting this into our equation form, I know A of t is going to be 10,000 or my final amount. The little a or my initial amount was 5,000. My rate is 0.0625. Remember, I'm putting that percentage as a decimal. And t is what I don't know. T is the number of years. That's what I'm solving for. I don't know how many years it'll take for a bank account to grow to that amount. In equation form, it actually looks like this. 10,000 equals 5,000, 1 plus 0.0625 to the t power. Now, how do we solve that? This is where, if you have good skills using your graphing calculator, this problem becomes a lot easier. You actually have problems like this on the SATs all the time. Here's a quick little shortcut you can use your graphing calculator to help you solve. So first, we're going to go to y equals, right, to the graphing part. I'm going to type in the equation of y equals 5,000, 1 plus 0.0625, that was the rate, to the t power. Now, even though we said it's to the t power, in your graphic calculator, the independent variable is always marked by x. And I hit graph. Now, I intentionally did this. Notice nothing is showing up. That might happen on your graphing calculator. If nothing is showing up in your graphing calculator, sometimes it's because your window is too small. Right now, my graphing calculator is only showing me from -10 to +10. Well, my initial value is 5,000. So I need a lot more than 10 showing up in my calculator. Hit the window button. In your window, it has x minimum. We're going to change that to 0 because I don't need negatives. We're going to change the x max. We'll put it all the way out to 50. My y minimum, well, we'll set it to 0 because I don't need any negative y values. My money is only going to grow. And we'll put the maximum at 20,000. Hit graph one more time. Now you can see that growth function. You can see the exponential growth of Clara's money. Now, I still don't know when this is going to hit $10,000. Here's a good trick to use your graphing calculator. If you ever want to know when a value or function is going to reach a certain amount, graph a second line as that number. So we're going to graph a line of 10,000. It's going to be a horizontal line because this is y equals 10,000. I can find where these two lines meet. Where those two lines meet is when Clara's bank account reaches $10,000. How do I figure out where these two lines meet? If you're using Desmos, you can actually just bring your mouse over and click on the point. You have a graphing calculator, you hit second, and this calc, which is above the trace button. And you have an option that says intersect. Your calculator is going to tell you where these two graphs intersect. You may have to move your cursor like I'm doing right now. You see that blinking dot? That's your cursor on the calculator. So I'm going to move it right down here so you can see it nice and clearly. See it blinking? My calculator is saying first curve. It's basically asking you to identify what is the first line that you want to consider for intersection. So we're going to hit enter, and it's going to jump to the second line. It says second curve. We're going to enter one more time. Then the prompt says guess. It's going to guess now where these two lines meet. They meet at exactly 11.433. See the y value is 10,000. All right, so that's a good trick to use for your graphing calculator. We're going to repeat that trick one more time. Let's just write this answer down. After, let's just say 11.4 years, Clara's account is worth $10,000. All right? Again, using the graphing calculator to help us. Or Desmos. Whenever I say graphing calculator, guys, Desmos is acceptable as well. We have one more example in the notes. Now we're going to talk about depreciation. Depreciation is exponential decay when the price goes down. So it says the value of a truck bought new for $28,000 decreases 9.5% each year. We're going to write an exponential function and graph it. Then we're going to use the graph to predict when the value will fall to 5,000. So the function we're going to write is y equals 28,000, or my initial amount, times 1 minus. Notice I'm using minus because it's exponential decay. 0.095, converting my percentage to a decimal. To the t power to represent that is going down 9.5% per year. This is what we're going to graph. Now, just for organization, I'm also going to be graphing y equals 5,000 and seeing where these two lines intersect one another. So I'm just going to clear out, that's my old lines, I'm going to clear all those out. 28,000, 1 minus 0.095 to x power. Make sure to hit that button, to the x power. I'm also going to graph y equals 5,000. Notice my line is exponential decay this time. The value of the truck is decreasing over time. That's my horizontal line of y equals 5,000. And let's figure out what is that value. Where do these 2 points intersect one another? So again, we're going to go to that trace button. Right above it says calc. So we get to that calc screen. Second calc. It says intersect. We're going to go use that intersect button. Look at my blink. I'm getting my cursor to somewhere you guys can all see it. It's kind of near the bottom. So now it's kind of in the middle of the screen. See it? So it's blinking. It's asking me to identify the first line that we're going to estimate where they intersect. Just hit enter. Or jump down to the second line. Hit enter. Hit enter again. Voila. It intersects. Where's the value at 5,000? Notice the y value is 5,000. It intersects when x is 17.26. We'll round it to. So after 17.26 years, the value of the truck is $5,000. And we know that. Think about a truck. If it's 17 years old, it's not really worth as much as if it was brand new. We all know that. All you guys are looking to maybe buy your first used car. Cars that are a little older or cost less money because they depreciate over time. We'll talk later on in the future about functions where some values then change to exponential growth, like when you have a classic car, like an old Mustang. But that's a lesson for another time. Use these notes in this video to help you solve the homework portion of today's lesson. If you have any questions, reach out to me.